Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through complex numbers. In our previous lessons, we've gone through the number systems, the row number systems, and we've looked at many properties as well as mathematical induction. In this lesson, we continue with complex numbers, which is another number category. Okay, so why complex numbers? In our first video, I made mention number systems are divided into two. So when you take number systems, it has two main branch. So it's either real or it's complex. And we've captured the real number systems thoroughly. Now, if you want to look at complex numbers, in our quest to find the value of square root of -1, square root of -2, square root of -3, and so on and so forth, we realize that it's very difficult to classify any of these numbers under real number systems. Because of that, we introduce what we call the complex operator I. You'll be seeing I a lot in complex numbers. It's called the imaginary. Okay, so you replace square root of -1, which is the minimum we can get with this. So whenever you see the I operator in complex numbers, is simply equal to square root of -1. Because of that, we can perform a simple mathematics here that I squared will be equal to -1. Okay, so whenever you see I squared is -1, whenever you see I is square root of -1, we'll perform some basic calculations on this very soon. But before then, let's analyze complex numbers well. Now that you've seen that I is equal to square root of -1, you realize that if you have square root of 2, you realize that if you have square root of 2 times square root of 3 in radicals, what do you get? Square root of 6, right? So if I have square root of -2, I can decompose this into square root of -1 times square root of 2. Hence, since I know that this root of -1 is I, my answer remains simple, square root of 2i. And this is what we call the complex number. It is a complex number, okay? So this is all that we'll be playing around throughout the complex numbers course. Now, generally, complex numbers have different representation, okay? So the popular one is the linear form. What we call the linear form. Linear form, okay? So the linear form of a complex number, and complex numbers are represented with z, okay? Just z. So if you have z is equal to a plus bi, then we say that this is a complex number notation. And through this give birth to a concept which is similar to what we do in linear graphs, Cartesian plane. We call that Argand diagram. So we have our Argand diagram. So the Argand diagram is simply a normal Cartesian plane, okay? It's simply a normal Cartesian plane with all the different sides. So these are 0 points, and we're going to have our real parts. Then this is our imaginary parts, negative imaginary and negative real parts. So whenever you represent a complex number in the linear form, such as z is equal to a plus bi, your a is a real part of the complex number, then your b is the imaginary part, where the I is a complex operator. A typical example is what we did here. When I give you square root of 2i, what I'm saying is this can be represented as 0 plus square root of 2i. And this is a linear form with real part 0 and the imaginary part square root of 2. So take note, imaginary part is always the value attached to the I operator in any complex number. So on the Argand diagram, let's say I use a simple complex number, z1 is equal to 2 plus 3i. What does that mean? On the real part, I have my 2. On the imaginary part, I have 3, right? So this will meet. And as we do it in the normal Cartesian plane, we connect this to the origin O, and this is our z1. So our complex number is OZ1, okay? And the distance from O to Z1 is what we call in complex number modulus. Modulus, okay? Take note, modulus, or which is also distance of a complex number. So you'll be calculating the modulus of a complex number. Then you can realize that there is an angular measure, theta, from the complex number plane to the real plane, okay? We call that the argument of a complex number. So these are few terminologies you'll be seeing in this number systems. So a complex number represented as a linear form can have its graphical representation, popularly called the Argand diagram. And within the Argand diagram, which has a linear form representation, we can derive what's another form called the polar representation. So polar representation. So with the polar representation, we simply say that we are looking at angular measure. Okay, so first of all, I made mention that the distance from this side to this side is what we call modulus. So it's represented as r, and it's called modulus of a complex number. Then the angular measure here is also what we call argument, represented as theta. So if I have z and I represent c as r angle theta, this is what this is what we call polar representation of complex numbers. So just at this point, you've realized that there are two main representations. We have the linear form, which is z equals a plus b. Then we have the polar form, right? Yeah, so let's move on gradually. Now, I made mention. Now let's go to some little computations here, which are few computation we're seeing. I said I is equal to square root of -1. I squared is equal to -1. In algebra, you'll be given problems where you have to simplify the I operator problems. Example, I'll give you I to the power 24. Solve this. What's the answer? To do this, you just have to simplify this using the basis. And the basis is that if I have I squared, it's going to give me -1. So how do I simplify this? The I operator to the power 24. That is simply equal to -1 to the power 24. And that is giving me, sorry. So whenever they give you this, first make sure you factorize your, so here you know that I squared is -1, right? We factorize I squared. So 24 is the same as 2 times 12. In indices, I'll get I squared to the power 12, which is literally multiplying the powers. So this still gives me what? I know I squared is equal to -1. I replace it with -1 to the power 12. Since 12 is an even number, then our answer will be positive. So we get 1. So I to the power 24 is simply 1. Okay. Some can ask you, what is I to the power 5? I to the power 5 is simply equal to I to the power 2, right? To the power 3. Or you can say that I to the power 2 multiplying I to the power 2 multiplying I, right? This gives us -1 times -1. This gives us this I is giving us square root of -1, right? That is negative I itself. So the answer here becomes -1 times -1 is what? 1 times I. So the answer is what? I. So I to the power 5 is the same as what? I. Take note of it. These are some petty computations, and we'll be solving more problems as the course move forward. Take note of that. Don't miss any part of our lessons. So now that you've seen the complex representation, the polar form, and the rest, now let's see the basic arithmetic properties which still holds in complex numbers. So in complex numbers, let's start with addition. Addition of complex numbers. Now, given a problem number 1, z1 is equal to 2 minus 3i, then z2 is equal to 4 plus 4i. Find z1 plus z2. What's the answer? So to solve this, we simply say that z1 plus z2 is equal to In the addition of complex numbers, take note, we add real parts together separately from imaginary parts, okay? Real parts separately from imaginary parts. So in this problem, you identify all the real parts you have. My real parts in the first complex number is 2. My real parts in the second is 4, right? My imaginary parts in the first is -3. My imaginary part is 4. So simply, I'll have z1 plus z2 is equal to 2 plus 4 in one bracket plus -3 plus 4 in another bracket with I. This simply gives us 6 plus I. That's all. So this is the answer for our simple arithmetic here. So whenever they ask you to find or to add any two complex numbers, it's very simple and direct. Add the real part together, then you add the imaginary part together. Then similar for subtraction, since subtraction and addition is just the same, we can try multiplication. So I have multiplication of complex numbers. So when it comes to multiplication, using the problem we had here, z1 times z2, how do we solve it? So giving 2 minus 3i is equal to, giving z1 equals 2 minus 3i, z2 as 4 plus 4i, then what is their product going to give us? So the product is simply going to give us, now you multiply 2 minus 3i, close bracket 4 plus 4i, right? So this simply gives us, you multiply the real parts, so it's the same thing we do. So 2 will multiply the entire 4 plus 4i, minus 3 will also multiply 4 plus 4i. What do we get? 2 times 4 is 8 plus 8i minus 12 minus 12i. At this point, it simply becomes addition and subtraction once again. You pair real parts and imaginary parts separately. So I have 8 minus 12 plus 8i minus 12i. What do I get? -4 minus 4i. As simple as that. This becomes a product. So this is the simple way to manipulate complex numbers. It's not difficult at all. Then finally, let's check about quotient or division, okay? Division here. Division. So for division, since I have z1 to be equal to 2 minus 3i, then I have z2 to be equal to 4 plus 4i. How do I divide this? So as usual, you have z1 over z2 to be equal to 2 minus 3i all over 4 plus 4i. But how do I divide this? Look at how it is. Because of this, we use a concept called conjugate. Conjugate, let me introduce this. Conjugate, okay? A conjugate of a complex number is simply the reversed sign of its imaginary number. That is all. Given this z1, z2 value that we had, -4 minus 4i, if you are being asked to find its conjugate, it's simply -4 plus 4i. As simple as that. Given 2 minus 3i, if they ask you what is the conjugate of 2 minus 3i, the answer is 2 plus 3i. You just negate the imaginary part, that is all. The same for 4 plus 4i, you just negate the imaginary part. Now we apply the same thing to solve the quotient. So my z1 over z2 is simply equal to, I'll have the 2 minus 3i over 4 plus 4i. Then I multiply top and down with the conjugate of the denominator. The idea is to eliminate the whole fraction, okay? So to eliminate a fraction, we target the denominator so that it will go away. Now, what do I get? I multiply here. And what's the conjugate? 4 minus 4i over 4 minus 4i. As simple as that, okay? So now let's get back. At this point, numerator will multiply numerator, denominator will multiply denominator. I'll have 2 minus 3i multiplying 4 minus 4i all over 4 plus 4i multiplying 4 minus 4i. As simple as that. So let's simplify these quotients simply. So the numerator I'll have 2 multiplying the expression 4 minus 4i minus 3i multiplying the expression 4 minus 4i, then all over 4 plus, so all over 4, you first open the bracket here, so sorry, so you have 4, open bracket 4 minus 4i plus 4i, open bracket 4 minus 4i, right? So you simplify systematically so that you don't make a mistake. So the numerator will give us 8 minus 8i minus 12i. Then check something. Whenever you are multiplying two things, okay, and you are having I multiplying I, what do you get? Negative 1. Take note. If I multiply I, you get negative 1. So you realize that I had negative 3i times 4 gave me negative 12i. But negative 3i times 4i, what do I get? The neg 3 and neg 4 gives me positive 12, right? Open brackets, the I and the I gives me negative 1. Then all over what I have here, I'll have 16 minus 16i plus 16i. Then also 4 times 4 is 16. I'll have plus 16, open bracket. I have I times negative I. That will give me positive 1. Okay. So this is where I have 8. Then I have negative 12. That gives me negative 4. Right. Then I have negative 20i all over 16 plus 16, 32. Then I and this goes away, right? So at this point, you realize that I can take away 4 out. So I'll get 4 open brackets negative 1 minus 5i all over 32. 4 goes into itself 1 and goes here 8. So simply our quotient becomes negative 1 over 8 minus 5i over 8. As simple as that. So our real part is negative 1 over 8. Our imaginary part is negative 5 over 8i. And that is division of complex numbers. Having known division of complex numbers, we simply talk shortly about what we call the modulus of complex numbers, as I mentioned earlier. The modulus of complex numbers. Given the same formula, so I gave 2 minus 3i, z1 is equal to 2 minus 3i, z2 to be equal to 4 minus 4i. If you've been asked to find the modulus of z1, sometimes the question will say find the modulus of z1. Other questions will say find z1 put into 2 bars. It's the same thing. What's the formula? For any general complex number z1, which is in the form x plus iy, the modulo z1 is simply equal to square root of x squared plus y squared. You just square the real part, you add it to the square part of the imaginary. So this gives me square root of 2 squared plus open bracket negative 3 squared. And this is giving me square root of 4 plus 9. That is square root of 13 units. As simple as that. The same for this. The modulus of z2 is simply equal to square root of 4 squared plus negative 4 squared, and this gives me square root of 16 plus 16, that is 32, right? Square root of 32. So having done this, you get 32 units, and that is all about modulus of complex numbers. There is another part which is argument, but argument is a little bit controversial and sometimes cause misunderstanding. I want us to capture that specially in the next video, so please stay glued to your seat and follow the course systematically. Please subscribe, share, and also like the video if it meets your expectations. Thank you.